we have a definition for the conditional distribution. We have the conditional probabilities for the conditional distribution. We just take the kernel and hit it by h. So this looks way too abstract, but in any context you can figure out what I mean. So in this particular case, what would it be? You can see it over there, that abstract looking monster is what we just worked out before. So I was wrong about the 11 minutes. I have to do the setup first. But again, just like I said before, given x equals x, h of xt is h of x. And xt plus 1, you just plug this in, and you have an expectation. So just think of this as code. This crazy thing, this p of x to dy, h of y, this is just generic notation that's universal. If it's discrete, it's a sum. If it's a density like I wrote down before. It's just code. It's code for that in the linear case, for example. All right. So you'll need examples to get used to this, but that's it. And this is actually also written another way. So the dh is useful. I'm going to write this as ph of x. Or even p minus I hitting h evaluated at x. And this is what I'm going to torture with in the exam. I'm going to make you memorize this. So I said that some things don't require tuition. They require flashcards. And maybe not for general state spaces, but I want you to know when I write pH, I want you to know what I mean. So I'll send out a warning to everybody. Because I've taught this course, how old am I, 100? I don't know, but for 50 years. And I've never once gotten to the end of the year and had anyone learn the notation. And so I don't know what to do about it. And so I'm just going to use this opportunity, so I delayed the exam, to just make you over and over again, maybe just in a finite state space, over and over again, say pH means the conditional expectation of h of x t plus 1 given x of t equals x. And maybe my first question on the exam will be to write this down 100 times. It's notation. It doesn't require brains. I'm not a genius because I memorized this formula. And it's so useful. I mean, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 symbols compared to 1, 2, 3, 4, 5, 6. It's almost a threefold reduction in complexity. I cannot keep writing that and get anywhere. And yet, I find grad students so stubborn. They refuse to learn this little trick. And you'll see it's very natural notation. All right. So the generated derivative, we take differences, and this, basically it's this one-step transition operator. It's a thing of an operator. It takes functions to functions. It's a mapping from functions to functions. Now, you won't. So now the clock starts. It's 4:17. I'm not doing bad. I actually could make it. I'm gonna answer partially this question. Oh, but I can't erase this, can I? Well, you remembered it. And so what we're going to end up doing is looking at drift condition. The most basic thing you'll see in this field. All the cases when people want to get performance bounds, they use this drift condition. And in my book, it's called condition V3. All right, but I didn't invent it. It goes back to the 1930s. And it is, I want a non-negative function So I want a function v from the state space to the non-negative numbers. It's a Lyapunov function if you've seen these before. And a constant and then a room. It's approximately what's called condition V3 there. And I'll write it down here. All right. So it says that, so, you know, I'm substituting, this is for any function h, I've got this definition of a generator. I'm assuming I have a function which is non-negative. So it's, you know, I mean, typically it's going to be something that blows up for large states. We're looking at Rn, and it's going to blow up for large, like a quadratic or something like that. And I'm looking at the expected increment, and I want it to be very negative when the cost is high. So I want this function to, on average, to be crashing downhill whenever the cost is big. And then let's play with this. Oh, mine and Tweety. So you'll see M&T over the next few weeks. There's a fairly famous book by myself and Richard Tweety. The way it is, though, I mean, it was called The Bible for Economists by a Nobel Prize-winning economist while he was the president of the American Economic Association, you know, Tom Sargent. You know, I mean, so it's quite a famous book. I mean, so anyway, he didn't say a Bible. He said the Bible. I feel bad. I'm sorry, Tom. I shouldn't do that. It was very sweet of him to do that. Of course, he doesn't mean that there are lots of Bibles for economists, but he did say that in his review. So anyway, if you really someday get into this in an advanced way, you'd look at this book. But this is what you can do is you can iterate this monster. So remember, D or P takes any function or another function. So I can iterate this thing. And I realize I have left something out, but I don't care. Yeah, I definitely did. And I realize I have to step back up. This is not 10 minutes. I forgot there's a lot of background you need to come through. So what does this mean? So first of all, this is just rewriting this equation because I told you already that D was just P minus I, you know. But I can actually hit P on both sides because after all, PV is a function, so I can map it to another function, right? You know, if these are, you know, and then PV is a function, it's a conditional expectation. PC is a function, it's a conditional expectation. P eta bar, what the hell is that? Well, eta bar is a constant, so it's conditional expectations itself. So you can just replace that by eta bar. Take a look. PH is a conditional expectation of function one step in the future, given where I am right now. So if H doesn't depend on the state, it's just a constant. It's just a constant. But the thing is, what do I mean by P dot P? We will see that if I take P and I hit it with PV, then back there you knew, you said it almost. What is it? And I evaluated x. So v is a function of x. I hit it by p, I get a new function of x. I hit it by p again, I get a new function of x. And what is that function? What's its interpretation? So we knew what that is. PV was this expectation of x one step in the future. So we'll do this next time. I wanted to go through and just get a result out of here and not just give you definitions. So it turns out that when you iterate this kernel over and over again, you're taking longer and longer predictions. And I'll just show you that next time. All right? So right now you just have to believe me. Yeah, I mean, okay? All right. So what will happen if I do this? All right.
It is my books.
No, yeah, that's right. It's a vibe, that's right. That's right. So I'll write it like this. So p squared v, that's the notation I'll use for p times p. Let's call it p squared. Is less than that, but pv is already less than that. So just plug that in. So now, can you see where I'm going to go with this? I'm going to do it again, all right? You know, and I'm going to do this. I'll do it 100 times until you're so bored you want to kill me. I could hit this by p again, and you'd see the same thing would happen. So I won't do it to you. If I looked at p to the nv, I'd get an inequality that's less than or equal to v, and I'd get a sum of terms like this. And that is non-negative. Let's rewrite this.
That almost brings back like controllability, like that almost looks like in a way.
I don't know.
Controllability matrix.
Yeah, maybe, I don't know. Yeah, it comes from iterating linear systems. That's where the controllability matrix comes from. So I'm iterating a linear system in a way, where it's an inequality, it's not a system, so yeah. But it looks familiar. So this, again, this is faith-based science right now, but each one of these is a conditional expectation, right? That's a constant, and that's a conditional expectation as well. So let's put it all together. So I've got the expectation of v of x n plus the summation k equals 1 to n of c of xk given x0 equals x. What have I done? I've taken this monstrous thing here and I've taken it to the left-hand side. And that's less than or equal to n eta bar. All right. And oh yeah, I missed something, didn't I? What did I miss? Yeah. Right, and this again, that's greater than or equal to 0. So we might as well forget about it because we don't know anything about that. It's just getting in the way. And so what you get is the average cost So just basically take both sides, divide by n, throw away this annoying positive part. You know, if I throw this away, I preserve this inequality because I just make, I throw away a positive term, and that's less than or equal to eta bar plus 1 over n v of x. I just love this result. It's so. I mean, I know I lied. It's 4:28, so I'm 7 minutes late. And also I had to cheat a bit. I had to say we will see, But without really any thinking at all for a totally general state space Markov chain, if this Lyapunov condition holds, then you get a bound on the average cost given by this constant eta bar. And you also get a bound on the transients. So there's basically, if V of the initial condition is large, you have to wait, until it is much larger than that for that transient to disappear. All right.
Where did that eta come from?
V3. So your task is to construct a function V and a constant eta bar such that this inequality holds. And that's what we do all the time in control. You do that, it's just a standard trick. Well, let's do it. What about forget the linear system, look at the random walk. So we all know now.
Is that n, not eta? N eta bar or eta bar?
Doesn't matter, I'm just multiplying together. See, look, I had 2 here, and when I have n here, I'll have a, yeah. Oh, I see what you mean, it looks like an eta, yeah. Okay, yeah. And so here I just divide both sides through by n. Yeah, it still looks like an eta, and I get that. Yep.
In the middle board, second line, when you apply P to the inequality, why does it preserve inequality?
Yeah, good question. My God, thank you. It really comes back down to this. Yeah, awesome. So really, once you understand this better, you can see why it's preserved. It's the monotonicity of the conditional expectation. Yeah, no, that's great. Yeah, that's a good question. So this is slightly incomplete. We'll fill in the gaps. Yeah, I just wanted to get to some sort of punchline. That was the reason I jumped ahead. Yeah, no, we have to explain why P is. I mean, so the thing is that when it's a finite state space Markov chain, P really is a matrix with non-negative entries, and that's why. Yeah, and it really comes down to that P is like I know it's forget it. Think about the finite state space case. P is a matrix with non-negative entries, and so it preserves inequalities. But look at the Q. Somebody give me V. So this is a typical obsession in queuing theory. You take your cost function to be just x because you're interested in the mean, and then the average amount of people wait in line, and maybe you care about the variance as well. All right, that's so you don't have a quadratic cost function ever practically. Can anybody kind of think about what kind of Lyapunov function would work? We could just play. So this is linear. You could try a linear function. That's non-negative because our state space is non-negative.
So we can try like x transpose x.
It's scalar. Yeah. No. This is our Q. No, this is a reflected random walk. Yeah. Okay. It's not the linear system. It's just a reflected random walk. But you're right. We're going to do that as well. So this, you can imagine, is not going to work. And maybe you have that intuition. If we look at dv, well, so so v of x equals x. So just look at the increments. You can see we're in trouble because the difference of the increments is just going to be delta, except when it's 0. right? This difference is just the noise. So it's negative. You know, and so, I mean, of course, at x equals 0, we'll get a different answer because of the plus. But if we're getting a bounded thing here, and we want something that blows up, that's not going to work. So we've got to go to Caleb's suggestion. We need something that grows faster than linear if we're going to have any success. Yeah? You know, I'm really tempted. We have time. Let's look at the fluid model and look at the generator. Let me use different notation. I can't control myself. I've got to do it. Because it's really cumbersome to look at discrete stochastic models. But with the fluid model, it's really easy. And let's construct the Lyapunov function for the fluid model and then look at and see if it works for the stochastic. What do you think? And so let's use your suggestion was v of q equals q squared. All right? And so let's look at ddt of v of qt. Because we're claiming that the behavior of this, I showed you the behavior of this fluid model looked similar to the stochastic model. Let's check it out. This is completely unscripted, but let's do it. So but we can apply the chain rule. So we know that this is equal to the derivative of v with respect to q. So it's 2q times ddt of qt. And that's equal to q dot is minus mu minus alpha. So it looks like, yes, we have our cost function, right, for the fluid model, first of all, except it's scaled by something annoying. So it really looks like we should rethink and divide it by both mu minus alpha and 2. So let's put a 0 there. It was our first try, but it didn't work. And let's say actually replace that by v of q. I'll put a 0 there, you know. And v of q is just renormalized. And if you do that, you do get ddt of v of q of t is equal to minus c of q. Okay, when q is 0, something different happens. You know, it's like something funky happens. But forget that. All right. So derivatives are like differences. Let's try it out. So if you actually then go back to dv for the stochastic model, qt. All right? And do the same thing. So the 0 is annoying because of this reflection term, the positive term. So just ignore 0, you know. And so what you end up with is this is equal to there's a scaling. And then we have an expectation of just, what's xt plus 1? It's just x plus delta. Right. All right, so I've just plugged in what V is. It's just V of Q, or whatever V of X is X squared over a constant. And then X equals X, so I can just substitute because delta is independent of the past. All right. And you can unravel this, and it's really cute. It really is. I mean, just do it in your heads. Square this baby. What are we going to get? We're going to get 1 over 2 mu minus alpha, expectation, and it's expanded out. You know, we've got x squared plus 2x delta 1 plus delta 1 squared minus x squared, parentheses around the whole monster, right? You could square, you know, square some of two things. And you see something nice happens. The x squares cancel out. So those guys are gone. And we have our expectation of delta. That was our minus mu minus alpha. So I've got a minus 2 mu minus alpha x. That gives me that. And this annoying second moment term. It turns out to be mu plus alpha. Oh no, it's just 1. No, because it's white. Because it's 1. Remember, delta was either 1 or minus 1. So its square is 1 or 1. Yeah, that's why I really simplify things a lot. Yeah, you know. So the absolute value of delta 1 is just equal to 1. Always, yeah. So it's not even, there's no expectation there. And look, it cancels. It worked. So basically, by solving this this equation with equality for the fluid model, we just test it out and we find it works for the stochastic model. Unfortunately, we get a different number when x equals 0. We have to, it's annoying. Well, I don't want to go through it again. It's boring. But if we say, what happens if x equals 0? You have to then, this is no longer true. And so you get something a little bit bigger.
So that second term right there, like the 1 over 2 mu minus alpha, it's saying like we can't do better than that, right? Like that's the.
No, I don't know about that, but this looks like eta bar.
That's like threshold.
No. You change the subject. dv3, where'd it go? Right there. We're trying to solve this equation. Now forget any other context, because no thresholds or nothing. We want to solve that equation, and we have gone through it, and we seem to have solved with equality, but only for x equal to 1. All right. And it turns out for x equals 0, we get something a little bit bigger, and anyway. You have to, for x equals 0, if you look at dv of x, it turns out to be minus 0. Or maybe we can do it in our heads. What happens is you only count the upward thing, not the downward. And and you get something bigger. I don't know. You work it out yourselves. So we'll work it out later. You get some funky number here. You just have to work it out. So, where this is bigger than 1. So unfortunately, 0 kills you. You get this beautiful equality for all x equal to 1, but because of the fact that there's reflection, you get somehow this bigger number there. So what happens is you have to take that as eta bar. All right, and so there you have it. So for the MM1Q, you get exactly this result, right? Where this is quadratic in x, and you get a bound here which isn't quite right, which is some funky number like that. And you see but it doesn't matter what this is. What's really important is that when mu gets close to alpha, that cost blows up. The bound blows up, as it should. After all if mu is close to alpha, this drift is very, very slow. All right, so that's a lot to take in. So what I'm going to do is I'm going to step back after this and really dive into the finite state space case, where this is way more concrete. We don't care about stability anymore, because on a finite state space, everything is stable. But I want to be able to give you some insight there, and then we'll come back to all this more abstract stuff. But one of my goals, the goals are for you to understand the notation again. But again, really just, I don't know, maybe it's 2 flashcards, what I mean by P and D. And that's really the only funky notation. It just means the conditional expectation. It's P, D or P. But then I want us to understand the dynamics of this thing. So basically, what ends up happening is we have this nonlinear state space model. Our analysis becomes a linear system, because we're looking at products of matrices, basically. These P's are like matrices. And so obviously, if you're looking at stability of linear systems, you're going to look at eigenvalues and things like that. So I want you to understand that. I guess that's about it. So that's just a few weeks, and then that sets the stage for all the nonlinear filtering and estimation parts. All right. So I think that's a good time to end. I will hold office hours, but abbreviated, because I have my own crises, and there's no exam tomorrow. So I'll be happy to spend a bit of time if there are questions. But if it's about this, ask it now. Don't run now and ask me, what did you mean by X?
So,
Oh, good.
if you're open for Q&A now.
Oh, no, I was asking, but I